These are the implicit differentiation notes, trimester 2, day 12. I wanted to go through some of these quickly, either as a repeat for some of you or for those of you who may have missed class. What we're looking at is a different way of differentiating. It's doing derivatives. We're going to use the same rules we've used up until now, but when we have an equation that's in what we call implicit form, everything that we've done so far with derivatives, we've had our equations in explicit form. That is, y equals something, y equals something. So these are problems that we've done on the board, we've had on quizzes. In each case, if we plug in our x value, it spits out our y value. So y is equal to, we sometimes have equations though that are not in that form, but the y is buried in our equation. So in example 2, we see that we have x squared plus y squared equals 4. It's called an implicit form because the y is buried inside the equation. It's not y is equal to some expression. So first of all, what I want to do is I want to sketch the graph. Some of you will recognize that this is an equation of a circle in the form x squared plus y squared equals r squared. So our center of this circle is at 0, 0, and the radius is 2. So I know I'm going to have these points for the circle. I can sketch a circle in. That's not a very good circle, but we're getting the idea. Sketch in the circle, and if I were asking about the slope at x equals 1, I'd find that there are two different points at x equals 1. I've got this point up here and this point down here. And I would have, if I wanted to draw a tangent line at either of those points, I'd say that I'd have a tangent line that looks like something like that. And another one looks something like that. So I've got two different slopes. I've got the slope of this upper line that's a negative slope, and the lower tangent line has a positive slope. If I wanted to find that slope, the first way would be to solve for y. So if I have x squared plus y squared equals 4, I want to solve for the y, so I'm going to subtract the x squared from each side and take the square root of each side. So I've got y equals plus or minus the square root of 4 minus x squared. So two separate equations, I'd have y equals positive square root of 4 minus x squared, or y equals negative square root of 4 minus x squared. Well, of course, if I want to get a slope, if I want to take the derivative, I don't like this notation of having a radical, so I'll rewrite it into 4 minus x squared to the 1/2, or y equals negative parentheses 4 minus x squared to the 1/2. If I want to take the derivative, I'm going to have dy dx equals 1/2 of 4 minus x squared to the negative 1/2, and chain rule says I've got to multiply by the negative 2x. Or derivative of the second equation, negative 1/2 4 minus x squared to the negative 1/2, and again chain rule gives me that negative 2x. Looking at each of these two equations, if I want to find out what is the slope at 1, well, with the first equation, I'd have y equals 1/2 of 4 minus 1 squared to the negative 1/2 times negative 2 times 1 equals, I'm going to tidy this up a little bit. I'm going to put this 1/2 and make that the square root of 4 minus 1 is 3. And this negative 2 up top gives me negative 1 over root 3. For the second equation, instead of tidying up second, I'm going to look at this equation and rewrite it first. So I'm going to take this -1/2, put the -1/2. If I've got this parentheses to the -1/2 power, I'm going to put that on the bottom because the negative exponent. Put it back in the radical and put the -2x up on top. Tidy that up. Negative times a negative becomes a positive. X, the 2's cancel, and leaves me with the square root of 4 minus x squared. Put my primes back in there. dy dx. This should have been a dy dx. Plugging in the x equals 1 from up here, and I've got dy dx equals 1 over the square root of 3. So my slope, dy dx equals -1 over root 3. This must be this line. And the other slope, +1 over root 3, must be this line. Well, that was kind of a pain in the neck to have to solve for the y, then take the derivative of two separate equations, and then plug in the 1 for each of those two separate derivatives. So that is our segue for why we want to learn this implicit differentiation. So what we're going to do is let's go back to our original equation again. The x squared plus y squared equals 4. And we're going to take the derivative just as it is. We'll use our same derivative rules that we've had all along. And remember that if I have y equals ax to the n, I get dy dx equals a, and in this case because of the 2, times the 2, x to the 2 minus 1. If I had a u to the n, so this is something other than x. If I'm taking the derivative with respect to x, how does y change when x is changing? I'm going to have this a times the n. The u shows up again, n minus 1, but then I've got to multiply by the derivative of whatever this u thing was. Well, over here, if I come back to this original equation, this is easy enough. The derivative of x squared is 2x. The derivative of y squared, well, I'm going to apply the same rule that I've had all along. So I've got 2y to the first power, 2 minus 1. But then since y isn't just a plain old x, I've got to use my chain rule. And the derivative of y, well, I know the derivative of y is dy dx. And then the derivative of a constant is 0. If I want to see what dy dx is by itself, I'm going to subtract 2x from each side. So I've got 2y dy dx equals -2x. Divide by the 2y, and dy dx equals -2x over 2y, or just -x over y. Well, taking that derivative, I'm going to say is a lot easier than what we did up here. If I want to find the value of the slope of the derivative at x equals 1, I not only need to plug in the x value, but I'm going to need to plug in the y value. So to do that, I'm going to have to say if x equals 1, what does y equal? Well, coming back to our original equation, x squared plus y squared equals 4. If x is 1, 1 plus y squared equals 4, y squared equals 3, or y equals plus or minus the square root of 3. So I've got 2 points. I've got the point 1 comma root 3 and 1 comma negative root 3. If I plug those into my derivative, I've got dy dx equals -x, -1, over y is root 3, or dy dx equals -x, -1, over negative root 3 is a positive 1 over root 3. So the same answers, that I got up here, I just got them a whole lot easier here. The one extra step I had to do was to find out, well, what is the y value at each of these two x values? So I now know that this point must be the point 1 comma, and what was that y value? Root 3. And this must be 1 comma negative root 3. This slope must be the negative 1 over root 3, and this slope is 1 over root 3. I, of course, could rationalize those denominators, but I also just wanted to point out we could also really easily write the equation of each of these lines right now by using our point slope. So that's using implicit differentiation to find the derivative. On that last equation, we could solve for y. It was a bit cumbersome, we did it, but on this equation, if I asked you to solve for y, we'd be stuck. If we tried to factor out the y, we'd still have a y squared inside. It's just a pain in the neck. So if I want to try and find the derivative, implicit is the way we need to go on this one. So if I take the derivative and use the same derivative rules I've had all along, I'm trying to find out how y changes with respect to the change in x. And my computer is frozen. I apologize, the computer was frozen there, so I think you just had some dead space. I'm trying to find how y changes with respect to the change in x. So when I take the derivative here, I'm going to be using my regular derivative rules. So I've got 3y squared, but since y isn't x, I'm going to have to put in my du, which in this case is dy dx. For this next term, I've got to notice that they're multiplied, so I've got to use the product rule. So the first times the derivative of the second plus the second times the derivative of the first equals derivative of a constant is 0. Tidying up, I've got 3y squared dy dx minus x dy dx plus, minus y equals 0. So if I want to solve for dy dx, I've got to keep my two terms that have got dy dx's in them on one side and get the other term, my y term, to the other side. So I've got 3y squared dy dx minus x dy dx equals y. I'll factor out the dy dx and have 3y squared minus x equals y, and then divide by whatever's in that parentheses, and dy dx equals y over 3y squared minus x. So we weren't asked to find a value, and we weren't at some specific x value or y value. We were just asked to find the derivative, so we're done. In our next example, we're not asked to find how x changes with respect, or how y changes with respect to a change in x, but we're looking how both variables change with respect to some change in t. T could be a change in temperature, a change in time, something else that's defined as a t variable. But instead of finding dy dx, it's dy dt or dx dt. So in this case, neither an x nor a y is a t value, so I'm going to have to use the chain rule for both of these. So my derivative, same rules as always. I'm going to have the negative 9x squared, but because x isn't t, it's not the variable with which we're taking the derivative, we're going to have to multiply chain rule a dx dt. Second term, 2 times 2 is 4, y, and a dy dt equals 0. Now, if I were asked to solve for dx dt, I would solve and get this dx dt by itself. If I were asked to solve for dy dt, I would solve and get that dy dt by itself. Where we will be going with these problems is that we will, at future time, be told, well, what if x is 1, y is 3, dx dt is 0.5, find dy dt. We'll be given some kind of information like that. But for right now, if we're just asked to find dy dt, find the derivative with respect to t, that's all we need to do is just leave it in that form. Hope this helps. Talk to you later.